let's continue our discussion about fields. So last time we proved this so-called fundamental theorem of algebra. In fact, there is another fundamental theorem of algebra. It basically depends on who calls which one the fundamental theorem, which I will discuss a little later in the lecture. But like we saw last time, that every field has this nice property that a degree d polynomial will have at most d roots in it. Now the one immediate question is, of the given a degree d polynomial over a field f, it will have at most d roots. The question the next one would be exactly how many of those d roots are actually in the field. It is possible that there are 0 roots in the field. For example, if you look at polynomial x square plus 1 over the reals, it can have at most 2 roots, but actually it has inside the reals it has no roots. So the number of roots would be lying between 0 and d. Okay, and that's a very important part of investigations about polynomials over fields, and that also gives us a way to create more fields or extend a field. Okay, so let's look at that. So let's say we start with a field. And we consider f bracket x. This is the ring of univariate polynomials over the field f. This ring has some nice properties. It is, for example, fx is an integral domain. Every ideal of fx is principal. Moreover, the unique factorization property holds in fx. Note that here I am not saying that fx is just a Dedekind domain where the unique factorization or ideal holds, but element wise also, just like over z, element wise unique factorization property holds similarly here, not only over ideals. So in that sense, fx is very similar to the ring of integers. You should see that every ideal is principal, unique factorization property holds. It's an integral domain, which are all very nice properties of integers. The first one is quite clear. That if a be in fx and they are non-zero, then ax times bx, this polynomial will also not be 0. The reason is very simple. You take the highest degree term of A, highest degree term of B, their product will give the highest degree term of A times B, and that coefficient will be non-zero. So this is simply borrowing the fact that f is an integral domain, and therefore fx will also be an integral domain. So that takes care of the first property. The second one, every ideal in F is principal. So take an ideal of fx and take two elements of this ideal. Oh, not fx. It's in take two elements of the ideal. Now we have this operation available in fx over polynomials, that is, which is taking GCD of two polynomials. Just like we can take GCD of numbers, we can take GCD of polynomials. Okay, and let that be C. Then C divides AX and BX both. Right, or in other words, in addition, we can write C as some let's say alpha x AX plus beta x BX. Right. So this implies that Cx is also in the ideal I. This equation is essentially just a GCD algorithm that gives you this. So C is in the ideal, and both A and B are multiples of C. Right. So we can say that AX, BX are in the ideal generated by C. Okay. So with these two properties we are done, because now you start with, in the ideal I, the smallest degree polynomial that is present in the ideal I. Okay. Now take any other polynomial of the ideal I. So let's say assume that, let's say AX in I is the smallest degree Okay. Then what can we say about C? B is any other polynomial in the ideal I. C must have the same degree as A, and C divides A. That means C is just a constant multiple of A, right? Which means that B is in the ideal generated by B is in the ideal generated by C, and C is just a constant multiple of A. So principal ideal of C is same as principal ideal of A. So B is in the principal ideal of A, and B was any arbitrary polynomial in the ideal I. So this shows I is simply the principal ideal generated by A. And the third one, the unique factorization. Well, let's assume that A1x times B1x equals A2x times B2x. So there are here two factorizations of one polynomial, and we want to show that these are, before that I need to define the notion of irreducible polynomials, but okay, but that is already defined. Remember, I had defined the notion of irreducible element of a ring, which generalizes the notion of a prime number in integers. Irreducible element was an element such that whenever you write it as a product of two elements, one of those two elements is a unit. Okay. So suppose we can write a polynomial as a product of two irreducible elements, A1, B1, A2, B2. A1, B1 is one set of irreducible elements, A2, B2 is another set of irreducible elements. So now I want to show that this is the same, that is A2 is equal to either A1 or B1, and similarly B2 is either equal to A1 or B1. Okay. So consider GCD of A1, A2. What is this going to be? This is either, see, both A1 and A2 are reducible. Either the GCD would, whatever the GCD polynomial is, that divides both A1 and A2. So because they are irreducible, that GCD is either equal to A2 or 1. So if GCD is equal to A2, that means A1 is equal to A2 except a constant multiplier. So that is fine. Then of course we can argue the same way about B1, B2, and we are done. On the other hand, if GCD equals A2, we are done. If GCD equals 1, then consider GCD of B1, A2. Do the same thing. Again, this also will either be A2 or 1.
A2 will divide B1.
Yes, if it is A2, if it is A2, then A2 and B1, since both are reducible, are just a constant multiples of each other. That again the we will be done. Right? Otherwise, if this GCD is also 1, then that's a bad case for us. Right? Then what happens? We'll show that it's not possible. How do we show that it's not possible? GCD, that is GCD of A1, A2 is 1 and GCD of B1, A2 is 1. Let's look at what is GCD of A1, B1 with A2. And I claim that GCD of A1, B1 with A2 is 1. Why? Well, it's just a bit of calculation. GCD of A1, A2, 1 means what? Alpha A1 plus beta A2 is 1. GCD of B1, A2 is 1 means what? Gamma B1 plus delta A2 is 1. Okay. So just combine these two. Just multiply this with B1. So we get alpha A1 B1 plus beta A2 B1 is B1. And multiply this with gamma. Alpha gamma A1 B1 plus beta gamma B1 A2 plus delta A2 is 1. This is B1 and B1 you substitute in this, you get this equation. And this gives me alpha gamma A1 B1 plus beta gamma B1 plus delta A2 is 1. So this shows that GCD of A1, B1 and A2 is 1. And that's not possible. Because clearly A2 divides A1, B1 by the assumption. And that's it. It proves the theorem. Okay. So this ring Fx behaves very much like the ring of integers. Now let's consider now it's a general polynomial. Let Px be in Fx. This is a polynomial of degree t. And let's go back to that the fundamental theorem of algebra, where we are looking at the roots of this polynomial p in the field F. Okay. Since unique factorization holds, I can write P as let's say Q1x, Q2x, dot Qkx, where Qjx is irreducible. Okay, and this can be written uniquely. Now, if when can we say that P has a root in F? In terms of Q1 to Qk. Q has? Qi is in Fx. Each one of them is in Fx. See, the fact that I can write P as a product of this irreducible polynomial, each one of Qj is in Fx. So that's not it. Root of P will be root of one of them. That's clear, right? If P is 0, then one of them will be 0. That is one conclusion we can derive. But suppose alpha is a root of P and alpha is in F. Can we say something about the nature of this, at least one of these Qj's? See, just go back to this proof. If alpha was a root of P, then P I can write as this, and there, which is as x minus alpha times P hat x. Linear factor. So, if alpha is a root of P and alpha is in F, then one of these Qj's will be of degree 1. And alpha, it will be actually of the form x minus alpha, where alpha is a root. Any linear polynomial is irreducible, of course. Okay. Up to multiplication by units. Yeah, that multiplication by units is fine. So that tells us whether by looking at this factorization of P, we can see how many roots of P are in F. That equals the number of linear factors. Okay. So there is no guarantee that all of them are linear factors. So some of them may not be linear factors. So let's say, suppose Q1x has degree greater than 1. So it is not a linear factor. Okay. Now consider this ring. Fx quotiented with the principal ideal Q1. What can we say about this quotient ring? Sorry? Elements of this. It depends on the degree of Q1. Right? If the degree, let degree of Q1 be D1, then elements of F, let's call this, okay, I'm giving away the name, by name the nature. Elements of f hat have this form. They are, each element is a polynomial of degree at most d1 minus 1 with coefficients being in f. Because you are quotienting with q1, which is a polynomial of degree d. Quotienting with q1, take any element if fx, you can divide it. Just again the GCD trick will give you a polynomial. After dividing, they will get a residue which will be of degree less than d1, and that's the element in this. Okay. Strictly speaking, it's the element is this plus the ideal. The elements of this quotient ring have the form a plus I. So this is the a and plus the ideal. That plus ideal I am not writing just to simplify this, but you must keep in mind that the elements of this quotient ring are not polynomials, they are equivalence classes. Okay. What else can we say about f hat? We can say that f hat is a field. Q1x is irreducible, yes. That's by factorization here. It follows because this ideal generated by Q1 is a maximal ideal. We have seen it's a principal ideal, of course, it's a principal ideal, but it's also a maximal ideal because Q1 is irreducible. So if there is any other, take any polynomial that is not a multiple of Q1, his GCD with Q1 will be 1 because Q1 is irreducible, which means that this principal ideal generated by Q1 is maximum. And so f hat is a field. We don't need degree greater than 1, but what if Q1 had degree 1? What is f hat then? F hat is just isomorphic to f, because then elements of the form alpha 0 plus the ideal Q1, that is just f. Whereas if Q1 has degree greater than 1, then we get a field f hat which is not equal to f. It certainly contains f, but it contains elements more than f. Why are we sure that it contains elements more than f? Well, simply because all such elements are in the f hat of this, which are polynomials of degree less than d1, and these elements are not, two such polynomials are not same in f hat. In particular, a root of Q1 is in f hat. Do you see that? What plus 0? I didn't get that. Class corresponding to 0. That's not a root of Q1. No.
Q1x should be since you are presenting with Q1x.
Yes.
So that is the kernel, so it will map to 0 in f.
Yeah, Q1x will map to 0, so that's fine. But in f hat, I'm claiming. What I should have done instead is, that's an important point. Let me, instead of doing it with x, let's redefine f hat as f of y quotiented with q1 of y. It is the same field. Only thing that has happened is that instead of variable x, I am using variable y. So the same field in the sense that this f hat is, this field is isomorphic to the field that earlier defined. Okay, fine. Now I ask, what is a root of q1x in f hat? Okay. Consider q1 of y plus q1y. This is an element of f hat. Now I am writing it properly with the clear understanding that this is an equivalence class. This equivalence class is an element of f hat. So if you replace x by this element of f hat in Q1, what do you get? This would be Q1 of y plus a multiple of Q1. Q1 of y. You don't see that? Okay, let's do it more slowly. Let me erase this. Let q1 of x be this polynomial. Okay. And do the substitution. let's write I for this ideal. Is this? Fine. The moment I do this substitution, Q1 of y plus I is now becomes an element in the field f hat, because y plus I is an element in the field f hat, and I am just doing some addition multiplication using that element. So this is an element in field f hat. Which element is this? Let's carry out this arithmetic. This is the field, we can do the arithmetic, and we know exactly how do you do arithmetic on the quotient rings. This is same as multiplication would mean y plus I raised to the j is same as y to the j plus I. Correct? And this sum would be just the sum of this part plus I. This is Q1 of y plus I and this is I, because Q1 of y is contained in I. So therefore what we got was that Q1 of this element y plus I is I in f hat. So y plus I is a root of polynomial Q1 of x in the field f hat. Okay? So therefore we conclude that Q1 has a root in f hat, which means Q1 is no longer irreducible in f hat. So Q1 further factors in f hat. So I can write Q1 as its irreducible factorization in f hat. At least one of those factors is linear. But there may be still some higher degree factors. So we can repeat this whole exercise with the higher degree factors. So this iterative process will eventually give me a field. Field, let's call it f bar. No, I don't want to call it f bar. F prime, such that all roots of p of x lie in f prime. there is a name for this particular field. It's called the splitting field of the polynomial P. All these fields that we get, starting from f hat and continuing all the way up to f prime, these fields are called algebraic extensions of the field f. We started with f, we took a polynomial which doesn't factor completely in f and used that polynomial to create a larger field and successively larger and larger fields, till the point that that polynomial factors completely. So all the fields that we get in this sequence are algebraic extensions. Yes.
We take polynomial x to the power 4 minus 1, then we have x square plus 1.
Yes.
This will give us a real number to complex.
That's right. That's right.
So those which were already linear in f.
Right.
So what will happen to them in extensions?
They will stay. Those roots stay. See, any extension contains the smaller field. Contains again in the isomorphic sense, right? Because now an element alpha of f in f hat becomes alpha plus I. That's the corresponding element in f hat, right? Because f hat is the quotient field, so every element is an equivalence class. So it's corresponding to alpha in f. The element in f hat is alpha plus I. Okay. So this is what an algebraic extension is. One of you asked in the last class, what is algebraic? How do elements of algebraic extension look like? This is exactly what they look like. They are polynomials of a certain degree in the base field, the starting field. The key thing is that we must start with the A field, look at the ring of polynomials, quotient it with an irreducible polynomial of degree more than 1. We get an extension field which contains the original field. Its elements are polynomials in the base field. Again, when I say polynomials, this is strictly speaking not true because they are equivalence classes of polynomials, but I am just going to continue saying it, they are polynomials because it's kind of easier to describe that way. Two fields are isomorphic, we take them to be equal. Well, not equal, you are right. They are not identical. But if two fields are isomorphic, then we can treat them as identical.
Can a ring be isomorphic to field? I mean, the ring does not have ring axis.
A ring, so if two rings are isomorphic and one of them is a field, the other has to be a field. Has to be there. See, the isomorphism means both addition multiplication are preserved. So if A times B is 1 in one, then phi of A times phi of B would be 1 in the other. So that means the inverses will also exist in the other. So in that sense, isomorphism essentially captures the same field. In fact, we have to use the notion of isomorphism just to take a side issue. why do we consider isomorphism? Well, let me define ring of integers as this. Okay, not integers are this is the usual way of defining a ring of integers. Let me define the following. This is a collection of different set of elements. The names, the symbols I am using are different. But the operations in both these rings are go in the essentially the same way. AI plus AJ is AI plus J. AI times AJ is AI times J. Would you say that this is also the ring of integers? It is. It's just that I am choosing, instead of choosing symbols 0, 1, 2 to represent numbers, I am choosing different symbols to represent the ring. But they are both, they represent essentially the same entity. So, and the only way I can establish the equivalence between them is through isomorphism. They are not equal, but they are isomorphic. And that's why when two objects, algebraic objects, are isomorphic, we treat them as identical. All right? Yes.
There was also a question how it is, we see algebraic extension as a vector space.
How do we see vector space? Now you tell me. Go back to the example. Consider f hat. What were the elements of f hat? F hat had as elements polynomials, in y of degree less than d1 plus I, of course. This I will ignore, continuing, because that's essentially the zero element. Now, if you just look at polynomials in variable y of degree less than d1, this forms a vector space over F. I can view F hat as a d1 dimensional vector space over the field F, with basis being 1 y square up to y1 to the d1 minus 1. Any element of f hat can be written as a linear combination of these d1 elements, and these are linearly independent also. So that's falls out of the way we have created extensions. Scalar multiplication is through f. Any element of f is treated as scalar here. Okay. So now the next question is, we now understand the algebraic extension of a field. Are there other types of extensions of a field? So you start with extension is basically start with a field and create a bigger field. So algebraic extension, we have seen how to do that. There is one more very important type of extension of a field, which is called transcendental extension. So again, start with the field f, and let f hat be the field of all rational functions in the variable x over f. This field f hat is a transcendental extension of it. This is clearly not an algebraic extension. Firstly, it's an extension because f hat contains f. But there is really no polynomial involved in this extension. Another way of seeing that f hat is not a finite dimensional vector space over f. Because it contains polynomials of arbitrary high degree as elements. So non-algebraic extensions which give an infinite dimensional extension are called transcendental extensions. But this is not of much interest for us. So we will not really worry too much about this. Let's get back to the algebraic extension. So is it, and ask the following question, is it that we can do an algebraic extension from any field? That is, take any field, can we do an algebraic, find an algebraic extension of that field which is larger than this? The answer is no, for the simple reason, take a field, consider f, that's a starting. Take a polynomial and go to the splitting field of f with respect to that polynomial. Okay. Then take another polynomial over f prime and go to the splitting field of that polynomial with respect to f prime, and keep doing this process. So essentially just keep, of course this is an infinitely long process, but you will eventually have a field which contains roots of all polynomials in it. Okay. So add roots of all polynomials. This is little informal, that notion that I am giving you, because I am not precisely defining it. So let me, instead of that, let me just go to the definition. So we have a field F where every polynomial over F has a root in F. Then such a field is called algebraically closed field, because you cannot extend this anymore algebraically. You take any polynomial that has a root in F, take that root out, it gives you get another polynomial of lower degree that will also have a root in it. So every polynomial of degree d will have exactly d roots in this such a field F. And so it is not possible to algebraically extend such a field. And earlier what I informally talked about, keep extending it forever, gives a way to visualize that there exists a algebraically closed field. But that's kind of not a very concrete example. So in the next class I won't prove that actually. It's not. Let me just end up with a theorem. The field of complex numbers is algebraically closed. This is also called fundamental theorem of algebra. Sorry?
We can find d roots.
Yes. Every polynomial of degree d has exactly d roots over complex.